16,000 light-years away, something is counting. Every 44 minutes, without fail, it fires radio waves and X-rays directly at Earth. Each burst lasts exactly 2 minutes. Then, silence. Then it happens again. Scientists call it ASKAP J, but they cannot tell you what it is. It does not match any pulsar, any magnetar, any binary system we have ever seen. Some believe it could be a new kind of dead star. Others think it might reveal physics we have never imagined. If you enjoy unraveling cosmic mysteries with us, hit that like button and subscribe. We begin now. In late 2024, astronomers at the International Center for Radio Astronomy Research noticed something that should not exist. A signal appeared on their screens, disappeared, then returned. The pattern repeated, without variation. The Australian Square Kilometre Array Pathfinder telescope had been scanning the southern sky when it detected pulses of radio energy arriving with mechanical precision. Each one lasted exactly 2 minutes. The gap between them measured 44.2 minutes every single time. This timing is what makes scientists uncomfortable. Natural objects drift, stars wobble as they spin, orbits decay, magnetic fields fluctuate. Yet here was something in deep space maintaining a rhythm more accurate than most human-made clocks. The researchers checked their instruments. They reviewed their data processing. They looked for errors in the timestamps. Everything checked out. The source sits 16,000 light-years from Earth in the constellation Scutum. That means the light we see today left this object when humans were just beginning to develop agriculture. The radio waves completing their journey right now started traveling during the dawn of civilization, and throughout that entire journey, the source has been pulsing. On, off, never missing a beat. Radio telescopes detect invisible light. Our eyes cannot see these waves, but they carry information across vast distances. When charged particles accelerate in strong magnetic fields, they emit radio energy. Pulsars do this. So do some binary star systems. But those objects pulse rapidly, several times per second, or at most every few seconds. Nothing known to science maintains a 44-minute cycle. The team named it ASKAP J1832-0911 after the telescope and its coordinates on the sky. They began follow-up observations immediately. Every time they pointed instruments at that patch of space, the signal appeared right on schedule. You could set your watch by it. Then they checked archival data. The Murchison Wide Field Array, another Australian telescope, had been photographing that region of sky for years during survey work. The researchers went back through old observations. There it was. The same signal, same timing, going back years. This thing had been broadcasting long before anyone noticed. The brightness varied, but the period never changed. Some pulses arrived stronger than others. Over 6 months of observation, the overall intensity decreased substantially. Yet, the clock kept perfect time. 44.2 minutes, 2-minute bursts. Like a lighthouse in the cosmos, except lighthouses are built by intelligent beings with purpose. Scientists began proposing explanations. Maybe an ultra-slow spinning neutron star. Maybe a white dwarf binary, where 2 stellar corpses orbit each other. Maybe something involving magnetic field interactions they had never seen before. Each theory had problems. Each left questions unanswered. The regular timing suggested something spinning or orbiting. But 44 minutes sits in a strange zone, too slow for any neutron star rotation we have detected, too fast for most binary white dwarf systems. The object occupies a gap in our understanding, where known physics provides no comfortable answers. Then someone checked if any X-ray telescopes had looked at the same region. What they found made the mystery deeper. Space between stars is not truly empty, but it might as well be. The journey from this pulsing object to Earth covers 16,000 light-years. Imagine every year of human recorded history as a single mile. You would need to walk that distance 3,200 times to match the span this signal crosses. The radio waves and X-rays traveling toward us move at light speed, the fastest velocity possible in our universe, yet they still need 16,000 years to arrive. Light from this source that reaches your eyes tonight began its trip during the last ice age. Woolly mammoths still roamed Earth. Humans lived in small bands, hunting with stone tools. All of written history, every empire that rose and fell, every war fought and peace made, happened during the time these particular photons flew through the void toward us. The signal does not weaken much over this distance. Radio waves spread out as they travel, like ripples on a pond, but they do not disappear. The object must be phenomenally bright to remain detectable after crossing such an expanse. Astronomers measure this brightness in Janskis, units named after a radio pioneer. This source peaks at 10 to 20 Janskis during its active phase, making it one of the most luminous long-period transients ever found. Between us and the source lies mostly hydrogen. Individual atoms drift through the interstellar medium, maybe 1 per cubic centimeter. That sounds sparse, and it is, but multiply it across 16,000 light-years, and you accumulate substantial material. Radio waves pass through this gas with little interference, which is why radio astronomy can peer deep into our galaxy while visible light gets blocked by dust clouds. The signal also passes through our atmosphere before reaching the telescope. Earth's ionosphere, a layer of charged particles high above the surface, can distort radio waves. The ASKAP telescope sits in Western Australia, in a radio quiet zone protected from human interference. No cell towers, no radio stations, just red desert and scientific instruments listening to the cosmos. The source resides in our own galaxy, the Milky Way. That might seem close in cosmic terms, but our galaxy spans 100,000 light-years across. This object sits roughly 16% of the way from us toward the galactic center. Thousands of stars lie between us and it. Clouds of gas and dust obscure the view in visible light. Only radio and X-ray observations can penetrate the murk. 16,000 light-years also means we see this object as it was, not as it is now. Maybe it still pulses with the same rhythm. Maybe it stopped broadcasting 10,000 years ago and we will not know for another 6,000 years. Maybe it changed completely, evolved into something new, or died. We are watching ancient history play out in real time, delayed by the speed limit of the universe. The signal passed through regions where stars are being born. It skirted molecular clouds, those stellar nurseries where gravity pulls gas together into new suns. It traveled through territories patrolled by wandering black holes, invisible monsters that bend space itself. Yet the radio waves arrived intact, carrying their message across the void. And that message repeats every 44 minutes. For years, perhaps centuries or millennia, someone finally noticed. But noticing raised more questions than it answered, because the first surprise was just the beginning. The burst does not ease in or fade out gracefully. When the appointed moment arrives, the source switches on like someone flipped a switch. Radio emission jumps from nothing to maximum intensity within seconds. The signal holds strong for exactly 120 seconds. Then it cuts off just as abruptly. Silence returns for 42 minutes before the cycle begins again. This sharp on-off behavior tells scientists something important. Whatever mechanism creates these pulses must be incredibly efficient and tightly controlled. Random processes create gradual changes. Chaotic systems produce irregular patterns. This object operates with machine-like precision. During those 2 minutes of activity, multiple things happen simultaneously. Radio waves pour out across a range of frequencies. The emission is highly polarized, meaning the waves vibrate in organized patterns rather than random directions. This polarization indicates strong magnetic fields at the source. It also suggests we might be seeing beamed radiation, like a searchlight pointing momentarily in our direction as something rotates or orbits. The 2-minute duration is long enough to gather detailed data, but short enough to remain mysterious. If the pulses lasted hours, astronomers might assume we were seeing something orbit into and out of view behind a companion star. If they lasted milliseconds, the object would fit into known pulsar categories. 2 minutes occupies an uncomfortable middle ground. Scientists can break down each pulse into component parts. The radio emission does not arrive as a smooth signal. Instead, it shows structure. There are sub-pulses, variations in intensity from second to second within the larger 2-minute window. These fluctuations suggest complex processes occurring at the source. Maybe material falling onto a magnetic field, maybe electrons spiraling through twisted field lines, maybe something else entirely. The source also emits across multiple radio frequencies simultaneously. Low-frequency observations and high-frequency observations both detect the pulses. This broad-spectrum emission requires energetic processes. Slow, cool objects emit narrow ranges of light. Hot, violent events produce wide spectra. Whatever powers this source packs considerable punch. Temperature might seem like an odd concept for radio waves, but astronomers use something called brightness temperature to describe how energetic a source appears. This object shows brightness temperatures in the billions of Kelvin during active phases. For comparison, the surface of our Sun reaches only 6,000 Kelvin. The numbers imply extreme conditions, perhaps particles accelerated to nearly light speed. Every 2-minute burst also arrives at almost the exact same phase in the cycle. If you graph the signal over time, the pulses line up nearly perfectly. This phase stability means whatever clock drives this object is extraordinarily stable. Tidal forces, magnetic braking, gravitational interactions, all the factors that should cause drift over time, seem to have negligible effect. The window also matters because it defines what telescopes can observe. 2 minutes is long enough for multiple instruments to coordinate observations. It is long enough to take spectra, measure polarization, track variations in real time. But it is short enough that you must be watching at the right moment. Miss the window, and you wait another 44 minutes. This timing creates scheduling challenges. Telescope time is precious and competitive. Convincing committees to devote resources to watching empty sky 42 out of every 44 minutes requires strong justification. Fortunately, the regularity helps. Point the telescope, wait for the clock to tick down, and the source delivers every time. But the radio emission was only half the story. When researchers looked at the same region with different eyes, they saw something nobody expected. Radio waves are light that your eyes cannot detect. Imagine the electromagnetic spectrum as a piano keyboard stretching beyond what you can see in both directions. Visible light occupies just 1 octave in the middle. Radio waves fill the bass notes, lower in energy, longer in wavelength. Your FM radio picks up waves roughly 3 meters long. Cell phones use waves 10 centimeters long. The ASKAP telescope detects waves between 4 and 12 centimeters, right in the sweet spot for penetrating cosmic dust. These waves behave like visible light in many ways. They travel at the same speed. They can be focused with dishes and mirrors. They bounce off objects and cast shadows. But their long wavelengths give them special properties. They slip through gas clouds that would completely block visible light. They emerge unscathed from regions where newborn stars hide behind thick dust curtains. Radio astronomy began accidentally in 1933 when Carl Jansky, working for Bell Telephone Laboratories, tried to track down sources of static that interfered with radio communications. He built a rotating antenna and discovered a steady hiss coming from the direction of the Milky Way's center. Nobody paid much attention. The first radio telescopes were not built until after World War II, using surplus radar equipment. Modern radio telescopes do not look like the optical telescopes you might imagine. They are gigantic dishes, sometimes hundreds of meters across, that collect and focus radio waves onto receivers. The ASKAP telescope consists of 36 dish antennas, each 12 meters across. spread across 6 kilometers of Australian desert. They work together as one enormous instrument, combining signals to create sharp images. When radio waves from space hit these dishes, they get reflected to a central receiver. There, sensitive electronics amplify the signal and convert it into data. The process is similar to how a satellite dish on your house receives television signals, just far more sophisticated. Modern receivers can detect radio waves so faint that the total energy collected by all radio telescopes ever built amounts to less than the energy of a single snowflake hitting the ground. This incredible sensitivity is why astronomers discovered the pulsing source. Its radio emission, while bright by astronomical standards, would be completely undetectable without specialized equipment. The waves arrive carrying information about their origin. Frequency tells us about the energy of electrons that produce them. Polarization reveals magnetic field structure. Timing variations indicate movement or rotation. Radio observations also offer another advantage. They can happen day or night, rain or shine. Clouds do not block radio waves. Sunlight does not drown them out. Radio telescopes operate around the clock, continuously monitoring the sky. This is how researchers gathered years of data on the 44-minute cycle. The source pulses whether anyone is watching or not. The source broadcasts primarily in a narrow range of frequencies. This is unusual. Most radio sources produce either very broad emission across many frequencies or very narrow emission at specific frequencies determined by atomic transitions. This object does something in between, suggesting an emission mechanism that astronomers do not fully understand. Radio waves can also be measured for their polarization. Light waves oscillate, and polarization describes the orientation of that oscillation. This signal shows linear polarization, meaning the waves vibrate primarily in one direction. The degree of polarization is high, often 50% or more. Only magnetic fields can produce such organized emission. The field lines must be incredibly strong and remarkably ordered. All this information comes from invisible light, from waves longer than your hand stretching across the void. But radio was just the first surprise. When researchers looked at the same spot with instruments that detect even more energetic light, the mystery multiplied. NASA's Chandra X-ray Observatory happened to be looking at the same patch of sky purely by accident. Chandra orbits Earth in an elliptical path that takes it more than 130,000 kilometers from the planet at its highest point. From this vantage, high above the atmosphere that blocks X-rays, it can detect high-energy photons from cosmic sources. On the particular day in question, Chandra was observing a supernova remnant, the expanding debris cloud from an exploded star. That remnant happened to lie in the same region of sky as the radio source. X-rays are energetic. They carry roughly 1,000 times more energy than visible light photons, and millions of times more than radio waves. Creating X-rays requires violence. Hot gas, powerful magnetic fields, or particles accelerated to extreme speeds. In space, X-rays typically come from matter falling into black holes, surfaces of neutron stars, or gas heated to millions of degrees in supernova shocks. The researchers did not initially connect the Chandra data with the radio observations. They were two separate projects. But when the radio team published coordinates for their mysterious pulsing source, someone noticed those coordinates fell within a Chandra observation field. They pulled the data, analyzed the timing, and found pulses, X-ray pulses, arriving every 44.2 minutes, lasting 2 minutes, perfectly synchronized with the radio emission. This changed everything. Before, astronomers could propose that maybe the radio emission came from low-energy processes, perhaps electrons spiraling through relatively weak magnetic fields. But X-rays demand more dramatic explanations. Something at that location is accelerating particles to incredible energies or heating matter to temperatures where atoms are ripped apart. The X-ray emission is faint compared to the radio brightness, but it is definitely there. Chandra detected photons with energies between 0.3 and 8 kilo electron volt. These are soft X-rays, the lower energy end of the X-ray spectrum, but still far more energetic than anything your eyes can perceive. The flux varied from pulse to pulse, just like the radio emission, but the period remained constant. Detecting both radio and X-rays simultaneously provides crucial constraints on theoretical models. Any explanation must account for how the same object produces both forms of radiation in perfect synchronization. If they arose from different locations or mechanisms, you would expect time delays or phase differences. Instead, they arrive together, suggesting a shared origin. The phase alignment is precise. When plotted against the 44-minute cycle, the radio and X-ray peaks line up within measurement error. This means whatever process generates the radio waves also generates the X-rays, or they are both produced by the same underlying event. Maybe particles accelerated along magnetic field lines emit both types of radiation simultaneously. Maybe the same shock wave produces both. Chandra's narrow field of view made this discovery unlikely. The telescope observes only tiny fractions of the sky at once, while ASKAP scans huge regions. The probability that Chandra would randomly be observing the exact same spot at the exact same time as ASKAP detected the source is minuscule. Astronomers call this serendipity, but it might have been the most fortunate accident in recent astronomy. The X-ray data also revealed something else. Over the months of observation, both the radio and X-ray emission faded significantly. The source became dimmer, though the timing remained unchanged. This coordinated dimming in both wavelengths reinforces the connection between the two emission mechanisms. No other long-period transient has ever been detected in X-rays. This source is the first. That makes it either exceptionally unusual or suggests that other similar objects might also emit X-rays but have not been caught in the act. The Chandra observation was simply lucky timing, but luck raises its own questions. How many more of these things hide in our galaxy, pulsing away, unseen? Before 2022, astronomers did not know these objects existed. That year, researchers at the International Center for Radio Astronomy Research announced the discovery of a radio source that pulsed every 18 minutes. They designated it Gleam X J1832-0911. It appeared in survey data, visible for several months, then vanished. Nothing like it had been seen before. Pulsars pulsed every second or fraction of a second. This thing took 18 minutes between beats. The announcement sparked searches through archived data. If one existed, maybe others were hiding in observations nobody had thought to check for such slow periodicities. Teams around the world started reprocessing old survey data, looking for signals that appeared and disappeared on timescales of minutes to hours. They found more. ASKAP J1935+2418 emerged, pulsing every 54 minutes. GPM J1832-0911 showed up with a 22-minute period and turned out to have been active for at least 3 decades without anyone noticing. Chime J0630+25 appeared with a 7-minute cycle. Each discovery expanded the known population of these mysterious objects. Scientists coined the term long-period transients to describe them. Transient means the source turns on and off rather than shining continuously. Long period distinguishes them from millisecond pulsars and other rapid variables. The name is descriptive, but reveals nothing about what they actually are. Current catalogs list only about 10 confirmed examples. That sounds like a tiny population, but astronomers suspect it represents severe undersampling. These objects are difficult to detect. Most radio surveys take short snapshots of the sky. If the source is off during that snapshot, it remains invisible. You need repeated observations of the same region or continuous monitoring to catch them. The objects show diversity. Some pulse regularly for years. Others appear for weeks or months, then disappear, possibly forever. Some emit polarized radio waves. Others show less polarization. Some are bright. Others barely register above detection limits. This variety suggests long-period transients might not be a single type of object, but rather multiple types that happen to share the common feature of slow periodicity. None fit comfortably into existing categories. They are not classical pulsars, which are neutron stars spinning rapidly. They are not typical binary systems, where stars orbit each other. They are not magnetars, though some might be old magnetars that have evolved into a previously unknown state. They are not white dwarfs, though binary white dwarf systems remain a possibility for some. The existence of long-period transients challenges fundamental assumptions about compact objects. Neutron stars should slow down as they age, but no theory predicted they could continue emitting radio waves at such glacial spin rates. Their magnetic fields should decay. Their emission should shut off, yet here are objects apparently violating those expectations. Some astronomers propose that long-period transients represent multiple formation pathways converging on similar observational properties. Maybe some are ultramagnetized neutron stars. Maybe others are white dwarf binaries. Maybe a few are something else entirely that we have not imagined yet. All produce slow, regular radio pulses through different mechanisms. The rarity complicates study. With only 10 examples and each behaving slightly differently, drawing general conclusions is difficult. Astronomers need more detections. They need to observe known examples across multiple wavelengths. They need to search for patterns that might reveal underlying physics. Finding one that emits X-rays was therefore extraordinary. It provided the first multi-wavelength detection of any long-period transient. It offered the first glimpse of high-energy processes in these systems. It opened a new window into whatever strange physics makes these objects tick. But it also deepened the central mystery, because this particular source refuses to match any simple explanation. Pulsars are dead stars, spinning like cosmic lighthouses, and we know them well. When a massive star explodes in a supernova, its core collapses into a neutron star. These objects pack more mass than our Sun into a sphere roughly 20 kilometers across. They spin rapidly, sometimes hundreds of times per second, because as the core collapses, it conserves angular momentum. A slowly rotating star becomes a rapidly spinning neutron star, the same way ice skaters spin faster when they pull their arms in. Neutron stars have powerful magnetic fields, often trillions of times stronger than Earth's. As they rotate, these fields accelerate charged particles near their magnetic poles. The particles emit beams of radio waves. If Earth happens to lie in the path of those beams, we detect pulses each time the star rotates and the beam sweeps across us. This model explains thousands of pulsars. Their periods range from milliseconds to a few seconds. They slow down gradually over time as their rotation energy dissipates. They follow predictable patterns. The physics is well understood and matches observations beautifully. The 44-minute source cannot be this type of pulsar. The period is thousands of times too long. A neutron star, spinning once every 44 minutes, would rotate so slowly that it could not generate the magnetic field structure required to produce beamed radio emission. The dynamo mechanism that sustains pulsar magnetic fields requires faster rotation. Below a certain rotation rate, the emission should simply shut off. This shutdown is called the pulsar death line. As pulsars age and slow down, they cross this line and cease being detectable. The fastest spin period before death varies depending on magnetic field strength, but it is always much shorter than 44 minutes. No conventional pulsar theory allows for emission at such slow rates. Maybe the object is not rotating but rather orbiting. Binary pulsars exist, where a neutron star orbits a companion star. We see regular patterns from orbital motion, but 44 minutes is too short for most neutron star binary orbits. and the emission characteristics do not match binary pulsar systems. Some neutron stars accrete matter from companion stars. The infalling material releases energy, producing X-rays and radio emission. These are called low-mass X-ray binaries, or spider pulsars, depending on configuration. The 44-minute source shows some similarities, but the phase relationship between radio and X-rays is wrong. In accreting systems, you expect the X-rays to come from hotspots where material hits the neutron star surface, while radio emission comes from jets or the magnetosphere. The timing should differ. Here, they are synchronized. The radioluminosity also poses problems. During active phases, the source pumps out tremendous power in radio waves. If this energy comes from rotation, the neutron star would need to possess enormous rotational kinetic energy. But a star rotating once every 44 minutes has relatively little rotational energy. The numbers do not add up. The source would exhaust its energy reservoir far faster than observations allow. Pulsar emission is also typically very stable in frequency. Pulsars pulse like metronomes with extraordinarily precise timing. This source maintains precise period, but varies significantly in brightness from pulse to pulse and dims substantially over months. That variability is unusual for standard pulsars. The high degree of radio polarization matches pulsars well, suggesting magnetic fields are involved. The broadband radio emission is also pulsar-like, but these similarities make the differences more puzzling rather than less. It is as if this object wants to be a pulsar, but refuses to follow the rules. Astronomers tried fitting the data to every known type of pulsar model. They considered young pulsars, old pulsars, millisecond pulsars, magnetars, and exotic variants. Nothing worked. Each model either predicted properties not observed or failed to explain observed properties. This left two possibilities. Either the object is not a neutron star at all, or it is a neutron star doing something no neutron star has ever been seen doing before. Some neutron stars have magnetic fields strong enough to rip atoms apart. These ultramagnetized neutron stars are called magnetars. Their field strengths reach 10 to the 14th or even 10 to the 15th Gauss. Earth's magnetic field, for comparison, measures about half a Gauss. The Sun's field peaks at a few thousand Gauss. Magnetar fields are incomprehensibly powerful. Such fields distort even the vacuum of space. They create exotic matter states where electrons are forced into elongated orbits. They generate seismic storms in the neutron star crust, causing starquakes that release more energy in 1 second than our sun emits in 1 year. They accelerate particles to energies that produce gamma-ray bursts, visible halfway across the universe. About 30 magnetars are known in our galaxy. Most are young, only thousands of years old. They rotate with periods between 2 and 12 seconds, faster than the 44-minute source, but still slow compared to typical pulsars. They emit X-rays continuously from their hot surfaces and occasionally produce spectacular outbursts when their magnetic fields undergo sudden rearrangement. Could the 44-minute source be a magnetar? An old one, perhaps, that has slowed to an extraordinary degree and evolved into a previously unknown phase. The theory has appeal. Magnetars can produce both radio and X-ray emission. Their powerful fields could accelerate particles to produce the observed radiation. The high degree of polarization matches what magnetar magnetic fields would produce. Some magnetars show periodic emission, though at much shorter periods, but problems emerge immediately. Magnetar magnetic fields decay over time. After a few 100,000 years, they weaken below the strength needed to power high-energy emission. An old magnetar should be effectively dead, not broadcasting powerful radio and X-ray pulses. The 44-minute period suggests extreme age, which contradicts the observed activity level. Even if the field somehow remained strong, the rotation period creates difficulties. Magnetar emission models rely on the star's rotation to generate pulses. As the star spins, its magnetic field sweeps through space, creating electric fields that accelerate particles. Those particles then emit radiation. But at 44-minute periods, this mechanism becomes inefficient. The rotation is so slow that the generated electric fields weaken dramatically. Some astronomers propose that maybe the magnetar is not alone. Perhaps it has a companion star, and the 44-minute period reflects the orbital period rather than rotation. Material flowing from the companion onto the magnetar could provide energy. Magnetic interactions between the two objects might produce the periodic emission. This binary magnetar scenario helps with the energy problem. Accretion provides a power source independent of rotation. It explains why the source remains active, despite presumably being old. It can account for both radio and X-ray emission through different mechanisms operating in the system. However, observations contradict simple binary models. In typical accreting systems, the X-ray and radio emission come from different regions and show phase offsets. The X-rays originate near the neutron star surface, where infalling matter heats to millions of degrees. The radio comes from jets or the outer magnetosphere. They should not pulse in perfect synchronization. The spectrum of the X-ray emission also does not quite match expectations for an accreting magnetar. The temperatures are wrong. The flux is too variable. Something about the emission mechanism differs from known systems. Perhaps the magnetar hypothesis is partially correct. Maybe this is an old magnetar, 500,000 years or more in age, whose field has decayed significantly but remains stronger than typical old neutron stars. Maybe it is undergoing a late-life reactivation, drawing on stored energy in its interior. Maybe it wobbles as it rotates, creating complex emission patterns we have not seen before. All of these are maybes. The data does not decisively support or rule out the magnetar explanation. It remains one possibility among several, each with its own problems. Not all dead stars are neutron stars. Most stars, including our Sun, will end their lives as white dwarfs. When a star exhausts its nuclear fuel, it sheds its outer layers and leaves behind a hot, dense core, roughly the size of Earth, but containing about half the mass of the Sunday. This white dwarf cools slowly over billions of years, eventually fading to darkness. White dwarfs can have magnetic fields. Some possess fields thousands or even millions of Gauss strong. While that sounds impressive, it is still much weaker than magnetar fields. Nevertheless, these magnetic white dwarfs show interesting behaviors. They can produce periodic emission when paired with companion stars in binary systems. The 44-minute source might be a white dwarf binary, two stars orbiting each other every 44 minutes, locked in close embrace. One is a magnetic white dwarf. The other could be a low-mass red dwarf star or another white dwarf. Material flows between them, channeled by magnetic fields, creating the observed radio and X-ray emission. This model has precedent. Two other long-period transients have been linked to white dwarf binaries through optical spectroscopy. Gleam X J1832-0911 is associated with a white dwarf plus red dwarf pair orbiting every 2.9 hours. ILT J1101+5,521 also shows signs of a similar binary system. So, white dwarf binaries can definitely produce long-period transient behavior. Binary white dwarf systems can maintain stable orbits with periods matching the 44-minute cycle. The orbital mechanics work perfectly. As the stars circle each other, different parts of the system come into view. Emission could be beamed, so we see pulses as particular orientations align with Earth. The 2-minute duration of each pulse could represent the time that configuration remains favorable. Magnetic field interactions in such binaries can be dramatic. As the magnetic white dwarf's field lines sweep through the companion star or through material flowing between the stars, they accelerate particles. Those particles then emit radio waves. If the field is strong enough and the geometry right, X-rays could be produced simultaneously through synchrotron emission or by heating material to high temperatures where field lines collide. This scenario addresses the energy problem that plagues the neutron star models. Binary interaction provides a continuous energy source. Gravitational potential energy from infalling matter or tidal interactions can power emission for millions of years. The system does not rely solely on stored rotational or magnetic energy. The phase relationship between radio and X-rays also becomes easier to explain. In a binary, both emissions could originate in the same interaction region, naturally explaining why they appear synchronized. As the magnetic field sweeps past the companion, it triggers both types of radiation simultaneously, but significant problems remain. The magnetic field strength required is extreme for a white dwarf. To produce the observed radio and X-ray luminosities with the observed characteristics, the white dwarf would need a field of at least 100 million Gauss, possibly several hundred million. While magnetic white dwarfs with fields of 10 to 100 million Gauss are known, they are exceptionally rare. No confirmed white dwarf has a field strong enough to comfortably explain all the observations. The proposed field strength pushes beyond anything previously detected. It sits at the extreme upper end of theoretical predictions for white dwarf magnetic fields, perhaps beyond what current models allow. The variability over months also poses challenges. Why would a stable binary system dim significantly over half a year? Orbital evolution happens over millions of years, not months. Maybe material flows vary. Maybe the magnetic field itself changes. Maybe we are seeing precession, where the orbital plane wobbles. None of these explanations are fully satisfying. Optical observations have not yet identified a companion star. If a red dwarf orbits the white dwarf, it should be visible. The region is crowded with stars, making identification difficult, but future observations might resolve the issue. If no companion exists, the white dwarf binary theory fails. So this explanation, like the magnetar hypothesis, remains possible but problematic. Something about it is probably right, but something is also wrong. 44.2 minutes should not work for anything. The period occupies a gap in the distribution of known cosmic clocks. Pulsars pulse at milliseconds to seconds. Binary star systems orbit at hours to days. Nothing bridges that gap. The 44-minute cycle sits in a theoretical void where no standard astrophysical process operates. Consider rotation. A neutron star spinning once every 44 minutes rotates far too slowly to generate pulsar emission. The centrifugal forces are negligible. The dynamo that sustains its magnetic field should not function at such slow rotation rates. Even the most slowly rotating pulsars discovered so far have periods measured in seconds, not minutes. White dwarfs can rotate at any speed, but they rarely emit periodic radio signals. The few that do have rotation periods of minutes to hours and are all in binary systems where the orbital period drives the emission, not the rotation. A solitary white dwarf spinning every 44 minutes would be invisible. Consider orbits. Two objects orbiting with a 44-minute period must be very close together. Binary white dwarf systems with such short periods exist, but they are in death spirals. They lose energy to gravitational waves and slowly merge. Within a few million years, they will collide. Maybe the 44-minute source is such a system, caught in its final phase before merger. But gravitational wave emission predicts that the orbital period should change measurably over months or years of observation. The orbit should shrink, the period should decrease. No such change has been detected. The 44 minutes remain constant within measurement precision. If gravitational waves are draining energy from the orbit, they are doing so too slowly to detect, which suggests the system is not as close to merger as the short period implies. Maybe the period reflects something else entirely. Maybe it is a beat frequency, the result of two different periodicities interacting. Maybe it is a harmonic of some other process. Maybe it is the time required for magnetic field lines to reconnect after being stretched by tidal forces. These possibilities are speculative. No detailed models exist to test them. The regularity of the timing adds another layer of mystery. Over years of observation, the period has not varied by more than a fraction of a second. This stability suggests a stable clock mechanism, something not subject to random fluctuations or external disturbances. Rotation and orbits provide such stability. Few other astrophysical processes do. Timing stability also rules out some exotic scenarios. The source is not flickering randomly. It is not responding to variable accretion rates. It is not being modulated by interactions with surrounding gas clouds. Something at its core maintains iron discipline over the 44-minute rhythm. The 2-minute pulse duration is also significant. Why 2 minutes specifically? The ratio of active time to quiet time is about 1 to 22. This ratio does not match obvious geometric factors. If we were seeing something sweep across us, like a lighthouse beam, you might expect the ratio to relate to the beam width and viewing angle. But the numbers do not obviously correspond to simple geometries. Perhaps the pulse duration reflects how long material takes to flow along magnetic field lines from one part of the system to another. Perhaps it is the time required for magnetic energy to build up and release. Perhaps it is determined by the light travel time across some critical region of the system. All plausible, none confirmed. Astronomers have also checked whether the timing changes with frequency. Some pulsars show dispersion, where different radio frequencies arrive at slightly different times due to interaction with interstellar plasma. This source shows normal dispersion consistent with its distance, but the pulse itself arrives at the same phase across all observed frequencies. Whatever produces the emission operates coherently across the entire spectrum. The most frustrating aspect is that 44 minutes feels deliberate. It sits right at a value that maximizes mystery, short enough to demand compact objects, long enough to defy standard models, just long enough to make continuous observation challenging, but short enough that patient observers can catch multiple cycles in a single night. If the universe designed this source specifically to puzzle astronomers, it chose the period well. Radio and X-rays arrived together, not by coincidence, but by necessity. In multi-wavelength astronomy, different types of light often come from different regions of an object. When you observe an active galaxy, optical light comes from stars. Infrared comes from warm dust, radio comes from jets, and X-rays come from hot gas near the central black hole. Each wavelength tells a different part of the story. Emission from these different regions typically shows phase offsets. The X-rays pulse at one rate, the radio at another, or if they pulse together, one leads and the other lags because they originate in different locations and light travel time separates them. These offsets help astronomers map the geometry of the system. The 44-minute source shows no such offset. The radio and X-ray pulses are synchronized to within measurement precision. When the radio emission turns on, the X-rays turn on. When radio peaks, X-rays peak. When radio fades, X-rays fade. The correlation is nearly perfect. This phase locking tells scientists something critical. The radio and X-ray emission must originate in the same region or be produced by the same population of particles. They cannot be independent processes happening in different parts of the system. Whatever mechanism creates one creates both. Several physical processes can produce both radio and X-rays simultaneously. Synchrotron radiation is one. When electrons accelerate through a magnetic field at nearly light speed, they emit radiation across a broad spectrum. Lower energy electrons produce radio waves. Higher energy electrons produce X-rays. If a single population of electrons spans this energy range, you get both emissions naturally. For this to work, you need strong magnetic fields and efficient particle acceleration. The electrons must reach energies of at least 10 billion electron volts to produce the observed X-rays. That requires powerful accelerators, probably magnetic field interactions or shocks where plasma streams collide. The brightness ratio between radio and X-ray gives clues about the electron energy distribution. This source is much brighter in radio than X-rays, suggesting most electrons have moderate energies, while only a small fraction reaches the high energies needed for X-ray production. That is consistent with many acceleration mechanisms, where energy decreases with particle count at higher energies. Variability patterns also match. When the source dims in radio over months, it dims in X-rays proportionally. The ratio between the two remains roughly constant. This coordinated fading reinforces the idea that they share a common origin. If they came from different mechanisms, you would expect one to vary independently of the other. The high degree of radio polarization indicates that magnetic fields order the emission. The X-rays are less polarized, which is expected. X-ray polarization is difficult to produce and difficult to measure. But what little polarization is detectable in X-rays aligns with the radio polarization direction, another sign of shared origin. Timing on shorter scales also shows correlation. Within the 2-minute pulse, radio and X-ray intensity fluctuates second by second. These sub-pulse variations match between wavelengths. When radio brightness spikes, X-ray brightness spikes a moment later. The slight delay might represent light travel time across the emission region, or could be an instrumental effect. This level of coordination demands physical connection. You cannot have two unrelated processes accidentally synchronizing so perfectly over such long timescales. The 44-minute clock drives both emissions. The 2-minute activation window affects both. The month-to-month dimming impacts both. They are two manifestations of the same underlying phenomenon. But what is that phenomenon? Particles spiraling through magnetic fields explain the basic physics. But what creates those magnetic fields? What accelerates the particles? What establishes the 44-minute cycle? Phase locking answers some questions while raising others. It does, however, decisively rule out models where radio and X-rays come from different components. Any theory proposing that radio comes from one star in a binary while X-rays come from the other is immediately excluded. Any model with radio from jets and X-rays from an accretion disk faces severe challenges. The emissions are too tightly bound. This constraint eliminates many possibilities. It narrows the field of viable explanations. But it does not point uniquely to any single model. Magnetars can produce phase-locked emission. So can white dwarf binaries. So can other exotic scenarios. The phase locking is necessary for understanding the source, but not sufficient to identify it. What astronomers need is more data, more observations across more wavelengths, optical spectroscopy to identify companion stars, infrared observations to detect thermal emission, gamma-ray monitoring to check for even higher energy emission. Each new piece of information constrains the models further, but gathering that data requires coordination across telescopes worldwide, each with competing demands for time, and it requires the source to keep pulsing. The source is dying, or at least dimming, before our eyes. Between initial detection and follow-up observations 6 months later, both radio and X-ray emission decreased substantially. The source did not switch off completely, but became significantly fainter. The 44-minute period continued unchanged, but the amplitude of each pulse dropped to a fraction of its original strength. This behavior is unusual for long-period transients. Some LPTs have been observed for years with relatively stable brightness. Others appeared for weeks or months, then vanished entirely, never to return. This source occupies a middle ground, fading gradually rather than blinking out suddenly. Several explanations for the dimming are possible. Maybe the emission mechanism is running out of fuel. If the source powers itself through stored magnetic energy or rotational kinetic energy, those reservoirs might be depleting. Like a battery running down, the source produces less light as its energy reserve dwindles. Alternatively, maybe the geometry is changing. If we see pulses because some structure sweeps past our line of sight, and that structure is precessing or wobbling, it might gradually point away from Earth. We would observe dimming as the beam misses us by increasingly larger margins. Eventually, it might miss us entirely, and the source would disappear from our perspective, even though it continues emitting. Another possibility involves the environment. Maybe the source is moving through a region of denser gas. Interactions with that gas could disrupt the emission mechanism, or maybe the gas absorbs some of the radiation before it reaches us. Though this seems unlikely because radio waves and X-rays penetrate gas well, and we would expect different wavelengths to be affected differently, which is not what observations show. Binary orbital evolution could explain the dimming if the source is a white dwarf pair losing angular momentum. As the orbit shrinks, the geometry of magnetic interactions changes. Maybe the shrinking orbit is transitioning the system from an active state to a quiescent one. Maybe we are witnessing the final stages before the binary becomes undetectable. The coordinated dimming of both radio and X-rays argues against simple absorption or geometric effects. Both wavelengths fade proportionally, maintaining their relative brightness ratio. This suggests the emission mechanism itself is weakening rather than the radiation being blocked or beamed away from us. Temporal variations over months are common in many astronomical objects. Young stars flare and fade as their accretion rates fluctuate. Variable stars pulse with regular periods but changing amplitudes. Active galactic nuclei brighten and dim over years. The 44-minute source joins this cast of variable phenomena, but long-period transients were supposed to be stable. They were supposed to pulse regularly with consistent brightness for extended periods. The fading challenges that assumption. Maybe LPTs are inherently variable. Maybe they have life cycles. Maybe they turn on, shine for years, then fade back into obscurity. If so, astronomers face a detection challenge. These objects might spend most of their existence in dim or dormant states, only occasionally becoming bright enough to notice. Surveys would then underestimate the true population, detecting only those currently in active phases. The galaxy might harbor hundreds or thousands of dormant LPTs, invisible to current instruments. The dimming also affects future observations. If the trend continues, the source might become too faint to study in detail within years. Researchers have a limited window to gather data before it drops below detection thresholds. This urgency has triggered a flood of telescope proposals, everyone trying to observe while they still can. Some telescopes are too insensitive to detect the source anymore. Chandra, with its small collecting area, can barely see the X-rays. Only long exposures catch enough photons for analysis. Radio telescopes with larger dishes still detect it clearly, but even there, the signal-to-noise ratio has worsened. If the source vanishes completely, it might return years or decades later. Some LPTs show this behavior, appearing intermittently. The first discovered LPT, Gleam X J1832-0911, was visible for only 3 months, then disappeared. It has not been seen since. Maybe the 44-minute source will follow the same pattern, or maybe it will fade to a stable low brightness state, still pulsing but barely detectable. Future telescopes, more sensitive than current instruments, might find it again and study its quiescent phase. Understanding both active and quiet states would illuminate the physics driving these objects. For now, astronomers watch. They monitor the fade. They take measurements while measurements remain possible, and they wonder whether they are witnessing a temporary fluctuation or a one-way journey into silence. The Australian Square Kilometre Array Pathfinder telescope sees more sky in a single glance than most telescopes see in a year. Located in Western Australia on Wajari country, ASKAP consists of 36 dish antennas spread across 6 kilometers of red desert. Each dish is 12 meters in diameter, relatively small by radio astronomy standards, but they work together as an interferometer. By combining signals from all dishes, ASKAP achieves the resolution of a much larger telescope while maintaining an enormous field of view. That field of view is the key. Most radio telescopes see tiny patches of sky, a fraction of a degree across. ASKAP can observe 30 square degrees simultaneously, equivalent to about 150 full moons side by side. This allows it to survey huge regions quickly, making it ideal for discovering transient and variable sources. The technology enabling this is called a phased array feed. Traditional radio telescopes use single receivers at the focus of each dish. ASKAP uses arrays of receivers, essentially multiple radio cameras per dish. Electronic systems then combine signals to create multiple beams, observing different directions at once. One telescope becomes many. This design philosophy reflects a broader trend in radio astronomy towards survey instruments. Rather than pointing at known interesting objects, modern telescopes scan the sky systematically, searching for phenomena nobody knew to look for. ASKAP embodies this approach. It takes radio photographs of large sky areas, then processes the data to find anything unusual. The 44-minute source appeared in one such survey. ASKAP was conducting a project called VAST, the Variables and Slow Transients Survey, designed specifically to find objects that change on timescales of minutes to days. The telescope repeatedly images the same regions of sky, comparing observations to detect changes. Most of the sky is stable. Stars do not flicker noticeably. Galaxies do not brighten, but occasionally something new appears. A supernova explodes. A star flares. A black hole turns on. ASKAP records these events, cataloging the dynamic universe. Processing the data requires sophisticated software. Millions of sources populate each image. Automated algorithms compare observations taken days or weeks apart, flagging anything that changed. The list of candidates then goes to human astronomers who examine interesting cases and decide which deserve follow-up. The 44-minute source did not appear as a steady object. It vanished between observations. This on-off behavior caught attention immediately. Further analysis revealed the periodic pattern. Once the period was known, researchers could fold the data, stacking multiple cycles together to boost signal strength. The source snapped into focus. ASKAP's remote location minimizes radio interference. Cell phone towers are absent, radio stations are distant, power lines are few. This radio quietness allows detection of faint signals that would be drowned out near populated areas. The Australian government protects the site legally, restricting radio emissions within a large exclusion zone. The telescope operates robotically. Astronomers in cities hundreds of kilometers away control it remotely, programming observations and monitoring performance. Data flows to computing clusters that process it immediately. Within hours of an observation, processed images are available for analysis. Each ASKAP dish can operate independently or as part of the array. This flexibility allows the telescope to simultaneously conduct multiple projects. Some dishes might observe pulsars, while others map hydrogen gas, while still others search for transients. This multitasking maximizes scientific productivity. The design anticipates the square kilometer array, a future telescope that will be 50 times more sensitive. ASKAP serves as a pathfinder, testing technologies and observing strategies. The lessons learned here will inform construction of the larger instrument. The 44-minute source discovery validates the survey approach and demonstrates the value of wide-field monitoring. Without ASKAP's unique capabilities, the source might have remained undetected for years. Traditional telescopes, pointing at known objects, would never have noticed a pulsing signal from a region nobody thought to observe. Only a survey telescope stumbled across it by accident, and only a coincidence brought the X-ray discovery. Chandra X-ray Observatory was not looking for the radio source when it found it. Launched in 1999, Chandra orbits Earth in an elliptical path that takes nearly 65 hours to complete. At apogee, the telescope reaches more than 130,000 kilometers altitude, about one-third the distance to the Moon. This high orbit places Chandra above the radiation belts that would interfere with its sensitive detectors. X-ray astronomy must be done from space. Earth's atmosphere blocks X-rays, protecting us from harmful solar radiation, but also preventing ground-based X-ray telescopes. Satellites like Chandra are the only way to observe this part of the electromagnetic spectrum. Chandra carries mirrors unlike any optical telescope. X-rays do not reflect off surfaces the way visible light does. They penetrate most materials. To focus X-rays, you must use grazing incidence mirrors, angled so X-rays strike at very shallow angles and skip off rather than passing through. Chandra's mirrors are nested cylinders, polished to atomic smoothness. The telescope has a small field of view, typically less than half a degree across. This is the trade-off for sharp resolution and sensitivity. Chandra takes detailed pictures of small regions rather than wide surveys. It studies individual objects in depth rather than scanning large areas. On the day it detected the 44-minute source, Chandra was observing a supernova remnant designated SNRG 22.7-0.2. This expanding cloud of debris from an exploded star lies in the same general region of the Milky Way as the radio source. Pure coincidence. The observation lasted several hours, much longer than the 44-minute cycle. During that time, the radio source pulsed several times. Chandra recorded X-ray photons arriving in bursts every 44 minutes, though nobody analyzing the supernova remnant data initially noticed because they were focused on the extended gas clouds, not point sources. The connection emerged only after the radio team published coordinates for their mysterious source. Someone compared those coordinates to archived Chandra observations and discovered the spatial overlap. They retrieved the data and performed timing analysis. The pulses appeared clearly. This serendipitous detection changed everything. Before, the radio source was interesting but not unique. After, it became the only long-period transient detected in X-rays. That uniqueness elevated it from curiosity to critical importance. Chandra's sensitivity made the detection possible despite the source's faintness. The X-ray flux measures only a few times 10 to the negative 14 ergs per second per square centimeter. That translates to about 1 photon detected every few seconds during active phases. You need long observations and careful analysis to pick out such faint signals from background noise. The telescope's timing accuracy is excellent. Each photon is time-stamped with precision better than a millisecond. This allows astronomers to measure the 44-minute period and confirm that X-ray pulses align exactly with radio pulses. Without precise timing, the correlation might have been missed. After the discovery, Chandra observed the source several more times. Each observation confirmed the 44-minute period. They also tracked the gradual dimming over months. The X-rays faded in lockstep with the radio emission, maintaining the same brightness ratio. Follow-up observations are competitive to obtain. Chandra is oversubscribed, with far more proposals for observing time than available hours. Convincing review committees to award time for this source required strong scientific justification. The uniqueness helped. This is the only LPT emitting X-rays, making it essential to observe while it remains detectable. The data collected includes not just timing and brightness, but also spectral information. X-ray spectra reveal temperature and composition of emitting regions. The spectrum of this source is soft, meaning most photons have relatively low energies. It can be fit reasonably well with models of hot plasma at temperatures around 10 million Kelvin, or with non-thermal emission from accelerated particles. Different spectral models have different implications for the emission mechanism. Thermal emission suggests hot gas, perhaps heated by shocks or magnetic reconnection. Non-thermal emission implies particle acceleration, synchrotron radiation from electrons spiraling through magnetic fields. The data does not clearly distinguish between these, leaving room for multiple interpretations. What Chandra definitively proved is that high-energy processes operate at this source. Whatever produces the radio waves also generates X-rays through violent energetic mechanisms. This is not a cool, quiet object. It is an engine of particle acceleration and magnetic field interactions operating in extremes. And it all happened because two telescopes accidentally looked at the same place at the same time. The magnetic field strength required to explain this source approaches the limits of what matter can sustain. Magnetic fields are invisible but powerful. They guide charged particles, store energy, and shape the environment around compact objects. In everyday life, refrigerator magnets produce fields of about 100 Gauss. Earth's magnetic field at the surface measures about half a Gauss. These are minuscule by astrophysical standards. Sunspots contain fields of a few thousand Gauss. These are strong enough to significantly affect plasma motion and energy flow. White dwarfs typically have fields ranging from 0 up to 1 million Gauss, though some rare examples reach 100 million Gauss or more. Neutron stars carry this to extremes, with typical fields of 1 trillion Gauss and magnetars reaching 10,000 trillion Gauss. To produce the observed radio and X-ray emission with the characteristics displayed by the 44-minute source, theoretical models require fields in the range of 100 million to 1 billion Gauss. This sits in an uncomfortable zone, too strong for typical white dwarfs, too weak for neutron stars, right at the boundary between two regimes. If the source is a white dwarf, it would rank among the most magnetic ever found. Fields above 100 million Gauss are extraordinarily rare for white dwarfs. Current theories struggle to explain how white dwarfs acquire such strong fields. Possibly, they inherit them from massive progenitor stars. Possibly field amplification occurs during merger events where two white dwarfs collide. Neither scenario is well understood. If the source is a neutron star, the field is surprisingly weak. Even old neutron stars retain fields of at least 1 billion Gauss. Fields below that threshold suggest extreme age, hundreds of thousands to millions of years. But such ancient neutron stars should be inactive. Their magnetic fields decayed to the point where they no longer accelerate particles efficiently. The required field strength also depends on geometry and emission mechanism. If the radio waves come from synchrotron radiation, charged particles must spiral through the field at relativistic speeds. The tighter the spirals and the more energetic the particles, the higher frequency radiation they produce. Producing both radio and X-rays from the same particle population requires a strong field and efficient acceleration. Magnetic field energy density can be enormous. In a field of 1 billion Gauss, the energy stored per cubic centimeter exceeds the rest mass energy of matter at normal densities. The field dominates the physics of the environment. Particles cannot move freely, but must follow field lines. Gas cannot flow perpendicular to the field, but streams along it. Fields this strong also affect atoms themselves. Electrons cannot orbit nuclei in the usual way. They are forced into elongated orbits aligned with the field. The energy levels shift, changing how atoms absorb and emit light. Spectroscopy becomes exotic, with features at wavelengths that would not occur in weak fields. Creating such fields requires either compression or dynamo action. Compression occurs when a star collapses. As radius shrinks, conservation of magnetic flux forces the field strength to increase. A star with a modest field spread over a large volume becomes a compact object with an intense field concentrated in a small region. Dynamo action involves fluid motions generating magnetic fields. Convection in stellar interiors or accretion disk turbulence can amplify weak fields into strong ones. But sustaining fields of 100 million Gauss or more requires specific conditions that are difficult to achieve and maintain. The stability of such fields is also questionable. Magnetic fields contain energy that can be released through reconnection, the process where field lines break and reform in lower energy configurations. Reconnection heats plasma and accelerates particles, exactly what this source seems to be doing. but repeated reconnection should eventually dissipate the field unless some mechanism continuously regenerates it. If the source is a binary system, magnetic interactions between the two objects could maintain field strength. Tidal forces stretch field lines. Orbital motion creates currents that amplify fields. The companion star might supply fresh magnetic flux through its own field or through plasma it sheds into the system. All these considerations make the magnetic field problem central to understanding the source. Get the field strength wrong, and nothing else works. Too weak, and you cannot produce the observed emission. Too strong, and you predict phenomena not observed. The field must fall in a narrow range, and that range happens to correspond to rare, extreme objects. Nature is good at producing extremes, but extremes are always rare. Whatever this source is, it occupies a regime of magnetic field strength where few objects exist. That alone suggests we are seeing something unusual, possibly a transitional phase or an evolutionary endpoint, reached by only a small fraction of compact objects. And the field alone does not provide answers. It is merely one piece of a larger puzzle. Power has to come from somewhere, and this source burns through it at an alarming rate. During its 2-minute active phase, the object emits approximately 10 to the 32 ergs per second in radio waves alone. Add the X-rays, and you push that number higher. Maintain this for millions of years, pulsing every 44 minutes without pause, and you need a staggering total energy budget. To put that in perspective, our Sun produces about 4 times 10 to the 33 ergs per second across all wavelengths. This source, despite being much smaller, briefly matches a significant fraction of the Sun's output in just radio and X-rays. Where does that energy come from? Several reservoirs exist in nature. Rotation provides one. A spinning object stores kinetic energy. As it slows down through friction or radiation, that energy converts to other forms. Pulsars tap rotational energy, gradually spinning down over millions of years as they beam radio waves into space. But a neutron star, rotating once every 44 minutes, has relatively little rotational energy compared to rapidly spinning pulsars. The energy stored goes with the square of the rotation rate. Cut the rotation rate in half, and you lose 3/4 of the energy. A 44-minute spinner has less than 1/millionth the rotational energy of a 1-second pulsar with the same mass and radius. That reservoir drains quickly if you are emitting 10 to the 32 ergs per second. Simple calculations show the source would exhaust its rotational energy in years, not the millions of years its existence seems to require. Either the source is incredibly young and we happen to be watching it during a brief active phase, or rotation is not the primary power source. Magnetic fields store energy too. A strong field represents compressed energy waiting to be released. Magnetars power their spectacular outbursts by tapping magnetic energy. As field lines twist and reconnect, they heat plasma and accelerate particles. For the 44-minute source, if the field is 100 million Gauss spread over a region 10 kilometers across, you can calculate the stored magnetic energy. It comes to about 10 to the 47 ergs. That sounds like a lot, but at 10 to the 32 ergs per second, the source drains that reservoir in roughly 300,000 years, possibly long enough, but only if the field does not regenerate. Gravitational potential energy offers another option. In binary systems, material can fall from one star to another. As it falls, gravity converts potential energy into kinetic energy and heat. This powers many bright X-ray sources in the galaxy. A white dwarf binary system, losing mass from one component onto the other, could easily power the observed emission. The gravitational well of a white dwarf is deep. Material falling onto its surface releases tremendous energy. Depending on the mass transfer rate, such systems can shine for millions of years before exhausting the donor star. But the observed emission characteristics do not quite match typical accreting systems. The radio brightness and the coordination with X-rays suggests something beyond simple accretion. Maybe accretion powers the system, but magnetic field interactions shape the emission. Maybe we are seeing a hybrid where multiple energy sources contribute. Tidal energy from orbital interactions could also play a role. As two objects orbit closely, they raise tides on each other. These tides dissipate energy through friction, heating the objects from within. Close binary systems lose orbital energy this way, slowly spiraling inward. The 44-minute orbit, if that is what the period represents, places the objects very close together. Tidal interactions would be strong. Energy dissipation could power emission. However, tidal heating typically produces thermal radiation, infrared light from warm surfaces. Converting that efficiently into radio and X-rays requires additional steps. Perhaps the answer involves multiple mechanisms working together. Orbital energy maintains the system. Magnetic fields channel and convert that energy. Rotation modulates the emission. Each component contributes, none sufficient alone but together, providing what the source needs. Or perhaps the source is inherently transient, destined to shine briefly and fade. Many astronomical phenomena are temporary. Supernovae explode once and fade over months. Novae flare and dim over years. Maybe long-period transients represent another class of temporary events, burning bright for decades or centuries before going dark. If so, we are fortunate to observe this one during its active phase. Most might be dark, their light shows already finished or not yet begun. The galaxy could contain thousands of former long-period transients, now silent and invisible. The energy problem does not have a definitive solution yet. Every model proposed faces challenges, explaining where the power comes from and how it is sustained. The source keeps broadcasting, indifferent to theoretical difficulties. The source sits in a crowded neighborhood where stars are born and die in cosmic drama. 16,000 light-years from Earth places it well within the Milky Way disk, that flattened region where most stars reside. The galaxy is roughly 100,000 light-years across, so this object occupies the inner regions, closer to the galactic center than to the edge. Specifically, it lies in the constellation Scutum, as seen from Earth. Scutum is not prominent in the night sky, a small constellation south of the celestial equator, often lost in the glow of the Milky Way band. But it occupies a significant direction, pointing toward the Scutum Centaurus arm, one of the spiral structures that give our galaxy its pinwheel shape. Spiral arms are not solid structures. They are density waves, regions where stars and gas clouds bunch together temporarily as they orbit the galactic center. Star formation happens preferentially in spiral arms because the increased density triggers gravitational collapse of gas clouds. Young, hot stars illuminate these arms, making them bright, invisible light. The 44-minute source resides in such a region. Surrounding it are stellar nurseries, places where stars are forming right now. Massive stars, short-lived and bright, explode as supernovae after only millions of years. Their remnants litter the area, expanding shells of gas and dust, enriched with heavy elements forged in stellar cores. This environment is also dusty. Clouds of microscopic particles block visible light, making optical astronomy difficult. Infrared and radio observations penetrate better. That is why radio telescopes like ASKAP are essential for studying objects in this direction. Visible light telescopes would see only obscuring haze. The galactic coordinate system places the source at roughly 22.7 degrees longitude and -0.2 degrees latitude. Longitude measures angular distance around the galactic center. Latitude measures height above or below the galactic plane. -0.2 degrees means the source sits almost exactly in the plane, embedded in the densest part of the stellar disk. This location has implications for the source's origins and evolution. Objects in the galactic plane tend to be younger than objects far above or below it. Old stars have time to drift away from the plane due to gravitational interactions. The fact that this source remains in the plane suggests it might be relatively young, perhaps only millions or tens of millions of years old, rather than billions. However, compact objects can remain in the plane even when old if they were not given much velocity at birth. Neutron stars usually receive kicks during supernova explosions, shooting them out of the galactic plane at high speeds. White dwarfs do not receive such kicks and drift slowly. If the 44-minute source is a white dwarf binary, its location in the plane is unsurprising regardless of age. The distance measurement comes from several indicators. Dispersion of radio waves provides one estimate. As radio waves travel through interstellar plasma, different frequencies arrive at slightly different times. The amount of dispersion depends on the amount of plasma between the source and Earth, which correlates with distance. Models of galactic plasma distribution convert dispersion into distance. X-ray absorption offers another clue. Gas and dust between us and the source absorb soft X-rays preferentially. The amount of absorption visible in the X-ray spectrum constrains the column density of material along the line of sight. Combined with maps of galactic structure, this also yields distance estimates. Both methods agree on roughly 15 to 16,000 light-years. The uncertainty is perhaps 20%, meaning the source could be as close as 12,000 light-years or as far as 20,000. Better distance measurements require parallax observations, watching how the source appears to shift position as Earth orbits the Sunday. That requires precise position measurements over years. Knowing the distance allows calculation of luminosity, the total energy output. Brightness tells you how much light reaches Earth. Luminosity tells you how much light the source actually produces. The difference is crucial for understanding the physics. A dim nearby object can appear as bright as a luminous distant one. At 16,000 light-years, the source radiates at the high end of what long-period transients produce. It is one of the intrinsically brightest examples known. That makes it either fundamentally more powerful than others, or oriented so its beamed emission points nearly toward us. The location also determines which telescopes can observe it. Southern Hemisphere observatories see it well. Northern telescopes struggle because it never rises high above their horizons. This geographical limitation means many of the world's largest telescopes cannot contribute observations, leaving the work to facilities in Australia, South Africa, and South America. But knowing where it is does not tell us what it is. Every astronomy textbook will need revision if this source represents a new phase of stellar death. We thought we understood how stars end. Small stars like the Sun swell into red giants, shed their outer layers, and leave white dwarf cores that cool slowly over trillions of years. Massive stars explode as supernovae, leaving neutron stars or black holes. The taxonomy seemed complete. We had mapped the life cycle from birth to death for stars of every mass. Long-period transients suggest we missed something. They represent behaviors not predicted by standard stellar evolution models. Either we are witnessing rare edge cases where unusual circumstances create unexpected outcomes, or we overlooked an entire phase that all stars of certain masses pass through. If the 44-minute source is an old magnetar, we are seeing neutron star evolution extend far beyond where theory said it should end. Magnetars were thought to be young objects, their intense magnetic fields, driving spectacular fireworks for thousands of years before fading into obscurity. Finding one still active after hundreds of thousands of years means magnetars last longer than predicted. Why would theory get this wrong? Possibly because magnetic field decay is more complicated than simple models suggest. Maybe fields do not decay monotonically, but undergo cycles of weakening and regeneration. Maybe crustal rearrangements in aging neutron stars sometimes reactivate dormant fields. We have observed only 30 magnetars, not enough to map their full life cycle. If the source is a white dwarf binary, we are seeing magnetic interactions in binary systems produce phenomena previously unimagined. White dwarf binaries are common. The galaxy contains millions, but only a tiny fraction show long-period transient behavior. What makes these special? Perhaps only binaries with extreme magnetic fields and precise orbital configurations produce observable emission. The parameter space is narrow. Get the orbital period slightly wrong, and nothing interesting happens. Make the magnetic field slightly weaker, and emission drops below detectability. Most white dwarf binaries are boring. A select few become cosmic lighthouses. This has precedent. Not all neutron stars become pulsars. Only those with strong fields and favorable spin axis orientations produce beams pointing toward Earth. Similarly, not all white dwarf binaries become long-period transients. Only those meeting specific criteria generate the spectacular periodic emission we observe. Stellar evolution is also sensitive to binary interactions. Most stars form in multiple systems. Companions affect evolution profoundly. They can strip mass from each other. They can merge catastrophically. They can exchange angular momentum and alter rotation rates. Many phenomena once attributed to single stars are actually products of binary evolution. The 44-minute source might be screaming that we need to think more about binary evolution. Perhaps these systems pass through a long-period transient phase as a standard step in their evolution. Every white dwarf binary with the right characteristics might someday become one. We only notice the currently active examples. If true, this means the galaxy is full of proto-long period transients, systems that will activate in the future, and post-long period transients, systems that have finished their active phase. Detecting these inactive examples would provide critical context. Are they common? Do they show distinctive signatures even when quiet? Theoretical astrophysicists are now racing to incorporate long-period transients into stellar evolution codes. These computer programs simulate stellar life cycles, tracking changes over millions of years. Adding new phases requires understanding the physics driving them. That understanding remains incomplete. Some researchers propose entirely new classes of objects. Maybe ultra-magnetized white dwarfs represent a distinct category. Not just white dwarfs with strong fields, but fundamentally different objects formed through special circumstances. Maybe neutron star white dwarf binaries, systems containing both types of compact object, produce long-period transient emission through unique magnetic interactions. Each new idea spawns predictions. If the new class exists, we should find examples showing specific properties. If particular formation pathways create long-period transients, we should see them in star clusters of certain ages, or in regions with specific metallicities. Testing these predictions requires surveys. The impact extends beyond compact objects. Understanding stellar death improves our knowledge of galactic chemical evolution. Dying stars enrich interstellar gas with heavy elements. The mechanics of that enrichment depend on what types of remnants form and how they evolve. Get the final stages wrong, and you misunderstand where elements come from. This is science at its best. An unexpected observation forces rethinking of established models. The models evolve to accommodate new data. Predictions emerge, tests occur, our understanding deepens. The 44-minute source is a teacher, revealing gaps in knowledge we did not know existed. But it will take years of work to fully integrate this discovery into the grand story of stellar evolution. One strange object is a curiosity, but 10 makes a pattern, and 100 would reveal the rules. Astronomers are now systematically searching for additional long-period transients. The goal is to build a large enough sample that statistical studies become possible. With only 10 examples, every object seems unique. With 100, patterns emerge. With 1,000, you can map the full diversity and identify subtypes. Several telescopes are dedicating observing time to this search. The ASKAP telescope continues its vast survey, imaging large areas repeatedly. The Meerkat telescope in South Africa, more sensitive than ASKAP, conducts similar surveys in the southern sky. The CHIME telescope in Canada monitors the northern sky continuously. These surveys generate enormous data volumes. Millions of sources appear in each observation. Software algorithms compare images taken days or weeks apart, identifying anything that changed. Most changes are instrumental artifacts or distant galaxies whose active nuclei fluctuated. Sifting through false positives to find real transients is laborious. Machine learning helps. Neural networks trained on known transients can recognize similar signals in new data. They flag candidates for human review. The process is not perfect, but it accelerates discovery. Systems that would take years to find manually appear within months. Early results suggest long-period transients are more common than initially thought. The first few discoveries seemed like rare flukes, but as search sensitivity improves and sky coverage expands, more candidates emerge. Some pulse regularly, others appear erratically. The diversity hints at multiple populations. Not all long-period transients emit X-rays. The 44-minute source may be unusual in that respect. Follow-up X-ray observations of other LPTs have not detected anything yet. Either their X-ray emission is much weaker, or they produce radio through mechanisms that do not generate accompanying X-rays. This raises the question of how representative the 44-minute source is. It might be an extreme example, brighter and more energetic than typical LPTs. Basing theories on it could be misleading if most long-period transients are qualitatively different. More detections across different wavelengths are essential. Optical identification provides another path forward. If researchers can pinpoint optical counterparts, companion stars in binary systems, spectroscopy becomes possible. Spectra reveal chemical composition, temperature, velocity. They can definitively identify white dwarfs or red dwarfs or other stellar types. Two LPTs now have optical counterparts. Gleam J0704-37 and ILT J1101+5521 have both been linked to binary systems containing white dwarfs and low-mass stars. Spectroscopy confirms the associations. These cases prove that at least some LPTs involve white dwarf binaries. But extrapolating from two examples to all long-period transients is risky. Maybe only a subset involves white dwarfs. Maybe others are solitary magnetars or exotic objects not yet imagined. The 44-minute source has no confirmed optical counterpart yet. Its crowded environment makes identification difficult. Many stars lie in the same region of sky. Which one, if any, is related? Higher resolution imaging could resolve this. The Hubble Space Telescope, or upcoming extremely large telescopes on the ground, could separate individual stars in the field. If one shows variability or unusual colors, it becomes a prime candidate for follow-up spectroscopy. Distance measurements for the growing sample will also illuminate their distribution. Do they cluster in the galactic plane or scatter throughout the galaxy? Are they associated with young stellar populations or old? Are they concentrated toward the galactic center or spread uniformly? Each distribution pattern implies different formation mechanisms. The 44-minute source sits in the galactic plane, suggesting relative youth or formation in dense stellar regions. If most LPTs share this trait, it points towards scenarios involving binary interactions in crowded environments. If others scatter widely, formation mechanisms might not require specific environments. Population statistics also constrain theories. If long-period transients number in the thousands galaxy-wide, they must form from relatively common progenitors. If only hundreds exist, they require special circumstances. Current estimates suggest the galaxy might contain 1,000 to 10,000 LPTs detectable with existing technology. Many more likely exist, but are too faint to observe. This implies that whatever creates long-period transients is not extraordinarily rare. Perhaps 10% of white dwarf binaries pass through an LPT phase. Perhaps all magnetars above a certain initial field strength evolve into LPTs given enough time. The progenitor population must be large. Finding more examples is not just an academic exercise. It is the path to understanding. Each new detection constrains theories. Each measurement of period, brightness, spectrum, or polarization narrows the parameter space. Eventually, only one explanation will fit all observations. The search continues. Two objects locked in mutual orbit create complex physics that single stars never experience. Imagine a white dwarf and a red dwarf star circling each other every 44 minutes. The orbital separation would be roughly 800,000 kilometers, less than twice the diameter of the Sunday. At this proximity, gravitational forces dominate. Each star raises enormous tides on the other. Tides on Earth create bulges in the oceans, pulled by the moon's gravity. Tides on stars do the same thing, distorting their shapes. The closer the stars, the stronger the tides. In a 44-minute binary, tidal forces are extreme. The stars elongate toward each other, becoming egg-shaped rather than spherical. These tidal bulges rotate with the stars, but not quite in sync with the orbit. Friction between the bulge and the rest of the star dissipates energy. That energy comes from orbital motion. The orbit gradually shrinks. The period decreases. Over millions of years, the stars spiral inward toward merger. This process is called tidal locking on timescales much shorter than stellar ages. The rotation of each star synchronizes with the orbital period. The same face always points toward the companion, just as the moon always shows Earth the same face. For the 44-minute binary, if this is the correct model, both stars rotate once every 44 minutes. But tidal locking is not the whole story. One star is a magnetic white dwarf with a field hundreds of millions of Gauss strong. That field extends far beyond the star's surface. It fills the space between the two objects. The companion star, or material flowing from it, moves through this field. When conducting material crosses magnetic field lines, it experiences resistance. The field exerts forces on the charged particles in the gas. Those forces channel the gas, making it flow along field lines rather than freely. Material spiraling toward the white dwarf cannot fall directly onto the surface. It must follow the twisted pathways defined by the magnetic field. This creates hotspots where field lines connect to the white dwarf surface. Material funneled along field lines crashes into these spots, heating them to millions of degrees. The hotspots emit X-rays. As the white dwarf rotates, the hotspots sweep into and out of view, creating periodic X-ray emission. Radio waves might come from a different region. Perhaps particle acceleration occurs where the magnetic field interacts with gas flowing from the companion star. Magnetic reconnection, where field lines break and reform, releases energy that accelerates electrons to near light speed. Those electrons then emit synchrotron radiation, producing the radio waves. The geometry of the system determines what we see and when. If the radio emission is beamed, like a lighthouse, we only detect it when the beam sweeps across Earth. The beam might be wide, lasting 2 minutes as it crosses our line of sight, with 42 minutes of darkness as it points elsewhere. The 2-minute duration could also reflect the time that the emission region is visible. Perhaps magnetic interactions happen continuously, but we see them only when specific structures rotate into view. Imagine a curtain of emission, aligned with the magnetic field. We see it when the curtain faces us, nothing when it is edge-on or facing away. Orbital dynamics also explain long-term variability. Orbits precess, wobbling like a spinning top. The orbital plane might tilt gradually over months or years. As it tilts, the angle from which we view the system changes. The beam might sweep across us less directly, causing the observed dimming. Eccentricity introduces another complication. Most close binary orbits are circular, but some retain slight elliptical shapes. In an eccentric orbit, the separation between the stars varies each orbit. When close, interactions intensify. When far, they weaken. This could modulate the emission strength on timescales matching the orbital period. If the 44-minute source is indeed a binary, both objects affect the motion. They orbit a common center of mass. More massive objects move less. Less massive objects move more. Precise measurements of the orbit could reveal the mass ratio, determining whether the binary consists of two white dwarfs, a white dwarf and a red dwarf, or some other combination. Such measurements require years of monitoring. Doppler shifts in spectral lines reveal orbital velocities. Changes in position on the sky, if measurable, show the orbital motion directly. So far, insufficient data exists for the 44-minute source. Future observations might provide the necessary precision. Binary evolution also predicts an endpoint. Eventually, the orbit shrinks enough that the stars merge. For a white dwarf binary, the merger might produce a supernova or create a massive single white dwarf. For a white dwarf-red dwarf system, the red dwarf might be completely disrupted, leaving only the white dwarf surrounded by a debris disk. How long until that happens? Gravitational wave emission and tidal friction both drain orbital energy. The timescale depends on the masses and separation. For the 44-minute orbit, rough estimates suggest millions of years remain before merger. We are witnessing a system in midlife, not its final moments. Understanding binary dynamics is essential for understanding the source. Every detail of orbital mechanics and magnetic interaction contributes to the observed emission. It is a complex, interconnected system where everything affects everything else. Converting stored energy into radio waves and X-rays requires specific physical processes. Synchrotron radiation remains the leading candidate. Electrons spiraling through magnetic fields at relativistic speeds emit photons. The frequency of emission depends on the electron energy and the field strength. Low-energy electrons produce radio waves. High-energy electrons produce X-rays. A population spanning this energy range naturally produces both. The mathematics are well understood. Give an electron with energy gamma moving through a field of strength B, and you can calculate the emitted power and frequency spectrum. Synchrotron emission is common in astrophysics. It powers radio galaxies, pulsar wind nebulae, and supernova remnants. Applying it here is straightforward, but several conditions must be met. First, you need a supply of relativistic electrons. Something must accelerate them to energies of at least 10 billion electron volts for X-ray production. Second, you need strong magnetic fields to make the electrons spiral tightly enough to radiate efficiently. Third, you need geometry that beams the emission toward Earth. Magnetic reconnection provides a likely acceleration mechanism. When magnetic field lines with opposite orientations come together, they can break and reconnect in a lower energy configuration. The released energy goes into heating plasma and accelerating particles. Reconnection occurs in solar flares, Earth's magnetosphere, and probably many astrophysical contexts. In the 44-minute source, reconnection might happen where the magnetic field of the white dwarf interacts with plasma from the companion star. The field lines, anchored in the white dwarf, collide with field lines in the infalling gas. They reconnect, launching electrons to high energies. Those electrons then spiral through the remaining field, emitting synchrotron radiation. The rate of reconnection could determine the emission brightness. Faster reconnection means more particles accelerated, brighter emission. Slower reconnection produces fainter emission. If reconnection rates vary over time, perhaps due to fluctuations in the mass flow from the companion, the observed brightness variations would be explained. Cyclotron emission offers an alternative. Electrons gyrating in magnetic fields emit at the cyclotron frequency, a specific frequency determined by the field strength and electron charge to mass ratio. For fields of 100 million Gauss, the cyclotron frequency falls in the radio range. Harmonics of the cyclotron frequency could produce emission at multiple frequencies simultaneously. However, cyclotron emission is typically weaker than synchrotron emission for relativistic particles. It dominates only when electrons have moderate energies, not the extreme energies needed for X-ray production. Synchrotron remains the better explanation for the overall spectrum. Curvature radiation is another possibility. Particles moving along curved magnetic field lines emit photons even without spiraling. The curvature of the field lines forces the particles to accelerate, and accelerating charges radiate. This process is important in pulsar magnetospheres. For the 44-minute source, if particles stream along field lines from the companion star toward the white dwarf, curvature radiation might contribute to the emission. But like cyclotron emission, it typically produces narrower spectra than observed. Synchrotron emission remains the most versatile explanation. Thermal emission could produce the X-rays. If material falling onto the white dwarf heats to tens of millions of degrees, it radiates thermal X-rays. The spectrum would be a blackbody or modified blackbody, depending on optical depth. Observations are consistent with this possibility, but thermal emission struggles to explain the radio component. Hot thermal plasma does not efficiently produce radio waves. You would need a separate mechanism for the radio, breaking the connection that phase locking implies. This is why non-thermal processes like synchrotron remain preferred. Coherent emission mechanisms exist but seem unlikely. Masers, for example, amplify radio waves through stimulated emission, producing extremely bright, narrowband signals. Pulsars might use coherent processes to achieve their extraordinary brightness temperatures, but coherent mechanisms are difficult to maintain over broad frequency ranges and extended time periods. The emission geometry also matters. If the radiation is beamed, only a small fraction of the sky receives the photons. Earth must lie within the beam to detect anything. Beaming naturally produces periodic emission in rotating or orbiting systems. As the beam sweeps past Earth, we see pulses. Beaming factors can be large. If the beam covers 1% of the sky, we detect only 1 in 100 such systems. The galaxy could contain thousands of similar objects, all beaming away from us, invisible to our telescopes. This greatly increases the true population compared to the number we observe. Alternatively, emission might not be beamed, but rather modulated by absorption or visibility. Perhaps we always receive radiation from the source, but surrounding material blocks it part of the time. As structures orbit or rotate, they move into and out of our line of sight, creating apparent pulses. This absorption model has problems explaining the sharp on-off behavior. Gradual changes in column density would produce gradual brightness changes, not the abrupt transitions observed. Unless the absorbing material has a sharp edge that cuts off the emission like a knife blade, absorption seems insufficient. Multiple mechanisms might operate simultaneously. Synchrotron produces the bulk of the emission. Thermal processes contribute to the X-rays. Geometric beaming shapes what reaches Earth. The full picture is probably complex, involving several processes working together. Distinguishing between these scenarios requires detailed observations. Spectroscopy reveals thermal versus non-thermal emission. Polarization measurements map magnetic field structure. Time-resolved studies track variability on short timescales. Each observable provides another clue. The emission mechanism is not just an academic question. It determines the physics, which constrains the object's nature. Get the mechanism right, and everything else falls into place. Get it wrong, and confusion persists. On the sky, the source appears to lie inside the wreckage of an exploded star, but appearances can deceive. The supernova remnant is designated SNR J1832-0911. It appears as a faint shell of expanding gas, the debris from a massive star that detonated perhaps 20,000 years ago. The shockwave from the explosion continues pushing through surrounding gas, heating it to millions of degrees and accelerating cosmic ray particles. Supernova remnants often harbor neutron stars or black holes, the collapsed cores left behind when the star exploded. Finding a pulsing object inside a remnant therefore seems natural. The explosion created the neutron star. The neutron star now broadcasts radio and X-ray signals. Case closed. but careful analysis suggests this connection is coincidental. The 44-minute source and the supernova remnant appear close together only from our perspective, like two buildings that appear to touch when viewed from afar, but are actually on different streets. The source and remnant might lie at different distances along the same line of sight. Distance estimates for the supernova remnant come from models of shockwave expansion and the gas density it is plowing through. These estimates place it around 10,000 light-years away, give or take several thousand. The 44-minute source, based on radio dispersion and X-ray absorption, sits at roughly 16,000 light-years. 6,000 light-years separate them. That is twice the diameter of the Sunday. They are unrelated, one behind the other, from our viewpoint, accidentally aligned on the sky. Several other factors argue against an association. First, supernova remnants fade over time. After 20,000 years, most are barely detectable. This one is faint, consistent with expected age. But a neutron star, born in that supernova, should be young and energetic, spinning rapidly and bright. The 44-minute source is slow and behaves like an old object. The timing does not match. Second, neutron stars born in supernovae typically receive kicks, velocities of hundreds of kilometers per second imparted by asymmetric explosions. These kicks send neutron stars flying away from their birth sites. 20,000 years at 300 kilometers per second carries a neutron star more than 6 light-years from the center of the remnant. The 44-minute source shows no obvious offset from the remnant center, but that proves nothing given the distance. Uncertainty. Third, if the source were born in the supernova, it should show chemical enrichment from the explosion. The supernova produced heavy elements that now mix through the remnant. A companion star inside the remnant would show traces of these elements in its spectrum. No optical identification of the 44-minute source exists yet, so this test has not been performed. Line-of-sight coincidences are not rare. The galaxy contains thousands of supernova remnants and thousands of compact objects. With both populations spread throughout the galactic disk, chance alignments happen regularly. Assuming connection without confirmation leads to errors. This is not to say the association is impossible. Perhaps the source is related to the supernova, just not in obvious ways. Maybe it is a runaway white dwarf binary that happened to pass through the remnant region. Maybe the supernova shockwave triggered something in a pre-existing binary system, activating the long-period transient behavior. Or maybe the supernova remnant is much closer than estimated, at the same distance as the source. Distance measurements have uncertainties. Models of remnant evolution make assumptions that could be wrong. Additional observations might revise the remnant distance, bringing the two objects into physical proximity. The Chandra X-ray Observatory initially targeted the supernova remnant, not the 44-minute source. The remnant was the object of interest. Detecting the pulsing source was accidental. This serendipity enabled the discovery, but also creates selection bias. We know about this source because it happened to lie in a field containing an interesting target. How many other LPTs hide in unmapped regions? Disentangling true associations from coincidences requires multiple lines of evidence. Distance measurements must agree. Ages must match. Chemical compositions should show connections. Kinematic properties like velocities must be consistent. For the 44-minute source and the supernova remnant, most of these tests are not yet possible. Future observations might settle the question. Proper motion measurements, tracking the source's movement across the sky over years, could reveal whether it is moving away from the remnant center, as expected for a kick. Spectroscopy of an optical counterpart could detect supernova enrichment. Refined distance estimates could confirm or rule out physical association. For now, the consensus leans toward coincidence. The source probably has nothing to do with the supernova remnant. It is a foreground or background object that happens to align with the remnant by chance. Nature plays such tricks regularly. reminding astronomers that seeing is not always believing. The next generation of telescopes will either solve this mystery or uncover 10 more just like it. Construction is already underway on the Square Kilometre Array, or SKA, a radio telescope that will be 50 times more sensitive than current instruments. Split between sites in Australia and South Africa, it will consist of thousands of antennas working together as one enormous instrument. When complete in the early 2030s, SKA will detect faint radio sources that are completely invisible now. Long-period transients are a key science target. SKA will conduct deep surveys, monitoring millions of sources for variability. Its sensitivity will reveal LPTs 10 times fainter than the 44-minute source. If these objects are common, SKA should find hundreds or thousands. If rare, it will at least detect the brightest examples throughout the galaxy and even in nearby galaxies. The increased sample size will transform understanding. With hundreds of examples, astronomers can measure distributions of period, brightness, polarization, and spectral properties. They can identify subtypes and trace correlations. They can test theories with statistical rigor rather than arguing over individual objects. X-ray astronomy is also advancing. Several next-generation X-ray observatories are planned for the 2030s. The Advanced X-ray Imaging Satellite, or AXIS, will combine Chandra's sharp vision with greater collecting area, detecting fainter sources. The European New Athena mission will conduct wide-field surveys while also providing spectroscopic capabilities. These telescopes will search systematically for X-ray emission from known radio LPTs. If the 44-minute source is typical, others should emit X-rays too. If it is unique, that uniqueness itself is informative. Either way, coordinated radio and X-ray surveys will provide the multi-wavelength data needed to constrain emission mechanisms. Optical astronomy contributes through spectroscopy. The extremely large telescope under construction in Chile will have a mirror 39 meters across, dwarfing current facilities. Its light-gathering power and resolution will enable spectroscopy of faint optical counterparts in crowded fields. Companion stars in LPT systems will be identified and characterized. Infrared observations will complement optical studies. The James Webb Space Telescope, already operational, can detect cool stars and warm dust that visible light telescopes miss. If long-period transients involve red dwarf companions or are surrounded by dusty disks, Webb will see them. Its spectroscopic capabilities can also reveal molecular features diagnostic of stellar types. Gravitational wave detectors are evolving too. The Laser Interferometer Space Antenna, or LISA, will launch in the early 2030s. Unlike ground-based detectors that sense high-frequency gravitational waves from merging black holes and neutron stars, LISA will detect low-frequency waves from binary white dwarf systems. If long-period transients are close white dwarf binaries, their orbital motion generates gravitational waves. LISA might detect these waves directly, measuring masses and orbital parameters with precision. The gravitational wave signal, combined with electromagnetic observations, would conclusively identify the systems and test general relativity in strong field regimes. Ground-based time-domain astronomy is expanding rapidly. The Vera Rubin Observatory, with its wide-field camera and rapid cadence, will photograph the entire visible sky every few nights. While designed for optical astronomy, it will identify variables and transients that can be followed up at other wavelengths. Unusual periodic sources will be flagged for investigation. Computational advances also matter. Machine learning algorithms are becoming sophisticated enough to search through vast datasets automatically. They can identify patterns human eyes would miss. As surveys produce petabytes of data, AI will be essential for extracting discoveries. Coordinated campaigns are already being organized. When one telescope detects a new long-period transient, alerts go out to observatories worldwide. Within hours, telescopes across the electromagnetic spectrum swing into action. Radio, optical, Infrared, X-ray, and gamma-ray observations happen simultaneously, capturing the full picture. This rapid response capability transforms transient astronomy. Instead of discovering something in archival data, months or years after it happened, astronomers catch events as they unfold. For objects that vary or evolve quickly, this makes the difference between useful observations and missed opportunities. The 44-minute source will remain a key target for all these facilities. As the first LPT with confirmed X-ray emission, it serves as a benchmark. Future observations will track whether it continues fading, brightens again, or stabilizes. Long-term monitoring over decades will reveal evolutionary timescales. These future observatories will also search for the youngest and oldest examples of long-period transients. Catching one immediately after it activates would provide snapshots of the initial conditions. Finding ancient examples, perhaps near the end of their active lives, would reveal endpoints. The full life cycle from birth to death will become observable. Within 10 to 20 years, the mystery of the 44-minute source will likely be solved. The question is whether the solution will be simple or whether it will open doors to even stranger phenomena. Sometimes, a single observation hints that the rulebook is incomplete. The 44-minute source does not obviously violate any fundamental laws of physics. It does not travel faster than light. It does not radiate more energy than mass energy equivalence allows. It does not contradict thermodynamics or quantum mechanics. Yet it pushes at the boundaries of what we thought possible within those laws. Magnetic fields, hundreds of millions of Gauss strong, approach the limits of what atomic matter can sustain. At even higher fields, atoms deform so severely that chemistry changes. Molecules cannot form. The vacuum itself undergoes quantum modifications, with virtual particle pairs affected by the field. The 44-minute source, if it harbors such fields, operates at the edge of this regime. Understanding these ultra-strong field environments tests quantum electrodynamics in conditions unreachable in laboratories. Particle accelerators on Earth cannot create sustained magnetic fields above a few 100,000 Gauss. Pulsed magnets briefly achieve millions of Gauss, but only for microseconds. Nature provides the only laboratory for studying billion Gauss fields. Observations of emission from such environments could reveal deviations from standard QED predictions. Does synchrotron radiation behave exactly as calculated in weak fields, or do quantum corrections appear? Do photons propagate differently through magnetized vacuum? These are questions physicists cannot yet answer confidently. Gravitational physics also comes into play if the source is a close binary. Gravitational wave emission at the predicted rates depends on general relativity being exactly correct. Detecting those waves with LISA and comparing to electromagnetic observations would test relativity in previously unexplored regimes. Any discrepancy, even a small one, would be revolutionary. Modified gravity theories make predictions differing slightly from Einstein's. Most have been ruled out by other tests, but some survive. A gravitational wave signal from the 44-minute source, deviating from general relativity predictions, would force reconsideration. The emission mechanism itself might involve new physics. If coherent emission processes operate, they could point to plasma instabilities not yet fully understood. If particle acceleration reaches energies beyond current models, new acceleration mechanisms might be at work. The details matter. Long-period transients also connect to the broader question of magnetic field generation and maintenance in compact objects. How do white dwarfs acquire billion Gauss fields? How do neutron star magnetic fields evolve over hundreds of thousands of years? These questions touch on magnetohydrodynamics, crustal physics, and stellar interiors. Each answer requires understanding matter under extreme conditions. Neutron star crusts, for example, are crystalline lattices of neutrons and protons at densities exceeding atomic nuclei. Laboratory physics cannot replicate such conditions. We rely on theoretical extrapolations, observations of objects like the 44-minute source, provide tests of those extrapolations. Binary evolution and tidal physics are well studied, but not perfectly understood. Close binaries lose energy to tides and gravitational waves, eventually merging. The timescales depend on mass, size, and internal structure. Discrepancies between observed and predicted evolution rates would point to missing factors in the models. The energy budget problem also has implications. If no conventional power source suffices, we might be missing something fundamental. Perhaps magnetic fields store energy in ways current theory does not account for. Perhaps matter, in extreme conditions, behaves differently than models predict. Perhaps particle physics beyond the standard model becomes relevant at high field strengths. None of these possibilities is likely. Physics is well tested. The standard model and general relativity have passed every challenge so far. But every test probes limited regimes. Ultra-strong fields, ultra-dense matter, and ultra-compact binaries extend beyond most laboratory and observational tests. They are where new physics, if it exists, might reveal itself. The 44-minute source also informs cosmological questions. Compact objects are remnants of stellar evolution. Their properties depend on the stars that created them. Those stars formed from gas, enriched by earlier generations. The chain extends back to the first stars in the universe. Understanding compact object populations helps trace galactic chemical evolution and star formation history. How many magnetars exist? How many white dwarf binaries? The answers constrain models of how galaxies evolve. They inform predictions about the distant universe, where we cannot observe compact objects directly. In a broader sense, every unusual astrophysical object is a natural experiment. We cannot build white dwarfs or neutron stars in laboratories. We cannot create magnetic fields strong enough to distort atoms. Nature does these experiments for us. Our job is to observe carefully and interpret correctly. The 44-minute source is one such experiment. It is showing us physics in action under conditions we cannot reproduce. Whether it confirms existing theories or reveals gaps is still being determined, but either outcome advances knowledge. This is why astronomers get excited about weird objects. They are not just curiosities, they are windows into fundamental physics, opportunities to test our understanding against reality. The universe is the ultimate laboratory, and we are fortunate to have telescopes that let us observe its experiments. The regularity feels too perfect, too deliberate, but it is not a signal from alien intelligence. Every few years, some astronomical discovery prompts speculation about extraterrestrial civilizations. Fast radio bursts did it. Tabby's star did it. Oumuamua did it. Now, some ask whether the 44-minute source might be artificial. The answer is no, with high confidence bordering on certainty. Several factors rule out artificial origin. First, the signal carries no information. It is simply periodic radio and X-ray emission, nothing more. No modulation patterns, no embedded messages, no structure suggesting intentional communication. It is a lighthouse, not a language. Second, natural astrophysical processes easily explain the periodicity. Rotation and orbital motion create periodic signals throughout the universe. Pulsars pulse, binary stars eclipse, asteroids reflect sunlight as they tumble. Periodicity is common, not rare or mysterious. Third, the physics operating at the source involves extremes incompatible with technology. Magnetic fields, hundreds of millions of Gauss strong, would destroy any conventional material. No known or imagined engineering could construct devices operating in such conditions. The radiation environment alone would melt or vaporize any machine. Fourth, the emission is incredibly energetic, but incredibly inefficient as communication. If an alien civilization wanted to send signals, they would use far less energy and far more structured transmissions. Beaming 10 to the 32 ergs per second randomly into space is wasteful beyond belief. Fifth, the location is unremarkable. It sits in the galactic plane among countless other stars, not near any special location or directed toward any particular target. If this were an intentional signal, you would expect it to be aimed somewhere or placed strategically. It is simply where some compact object happens to be. The SETI community, dedicated to searching for extraterrestrial intelligence, is not interested in the 44-minute source. It does not match any profile of what an artificial signal should look like. Researchers in that field know how to distinguish natural astrophysical phenomena from potential technosignatures. This is firmly in the natural category. Why does periodicity feel deliberate? Probably because humans are pattern-seeking creatures. We evolved to notice patterns in nature, to predict when fruit ripens or prey migrates. Regular patterns attract our attention and sometimes make us imagine agency where none exists. The 44-minute cycle is precise, yes, but so are countless other natural cycles. Earth's rotation is precise. Atomic clocks, based on cesium transitions, are even more precise. Precision alone does not imply design. It often arises from simple physics operating consistently over time. That said, astronomers do not dismiss the search for extraterrestrial intelligence. SETI is legitimate science asking important questions. If intelligent life exists elsewhere, it might produce detectable signals. We should look, but we should also recognize natural phenomena when we see them. The 44-minute source teaches us about stellar physics, magnetic fields, and compact objects. It does not teach us about alien civilizations. Conflating the two misses the genuine scientific value of the discovery. Interestingly, pulsars, when first discovered in 1967, sparked similar speculation. The regularity of the pulses seemed so perfect that researchers briefly considered artificial origin. They even nicknamed the first one LGM-1 for Little Green Men. Within months, more pulsars were found and natural explanations emerged. The regularity was understood as rotation, not signaling. Long period, transients are following the same path. Initially mysterious, they will eventually be understood as natural consequences of compact object physics. The mystery is not whether they are artificial, but exactly which natural process creates them. This distinction matters because public fascination with aliens sometimes overshadows real science. When media reports focus on mysterious signals without context, they create false impressions. The 44-minute source is mysterious in the sense that scientists have not yet fully explained it, but it is not mysterious in the sense of being unexplainable or supernatural. Nature is stranger than we imagine, but not stranger than we can understand. Given enough observations, enough data, and enough careful thought, natural phenomena yield to explanation. This source will too. The universe is full of wonders that need no embellishment. A dead star broadcasting with clockwork precision across 16,000 light-years is remarkable enough without invoking aliens. The real story, the astrophysical story, is more interesting than fiction. So, while speculation about extraterrestrial intelligence makes headlines, scientists focus on the actual physics. They measure magnetic field strengths, model emission mechanisms, calculate orbital parameters. They build understanding through observation and theory. That is how progress happens. And when the mystery finally resolves, when we understand what this object is and how it works, it will not diminish the wonder, it will enhance it. Knowing how nature creates such phenomena is more satisfying than leaving them unexplained. The answer is coming, but it will arrive from an unexpected direction. Perhaps the breakthrough will be technological. A new telescope with unprecedented sensitivity might detect dozens more long-period transients, revealing patterns invisible in the current small sample. Statistical analysis could show that all examples share properties suggesting a specific model. Perhaps it will be observational. An optical counterpart might finally be identified for the 44-minute source. Spectroscopy could reveal chemical signatures definitively linking it to a white dwarf binary or excluding that possibility entirely. A companion star's properties would constrain the system's mass and age. Perhaps it will be theoretical. Someone might develop a new model that naturally explains long-period transients without ad hoc assumptions. A fresh perspective on magnetic field, evolution, or binary interactions could illuminate what current theories miss. The solution might be simple once someone thinks of it. Perhaps it will come from another field entirely. Gravitational wave detections from LISA might identify binary systems with 44-minute periods, confirming orbital motion. Neutrino detectors might catch rare emissions from magnetic reconnection events. Gamma-ray observations might reveal even higher energy processes operating sporadically. Perhaps the source itself will change. If it brightens suddenly or shuts off completely, the transition would provide crucial information about its nature. If the period shifts detectably, that shift would reveal physical processes altering the clock mechanism. Variability constrains models as much as steady behavior does. Perhaps another long-period transient will do something spectacular. One might flare dramatically, releasing enormous energy in minutes. One might suddenly start pulsing after years of silence. One might explode or merge, revealing its true nature catastrophically. Such events would provide snapshots of extreme physics in action. Perhaps the answer is already in hand, buried in data nobody has analyzed correctly. Archives contain decades of observations from hundreds of telescopes. Reprocessing old data with new algorithms might reveal the 44-minute source was visible years before its official discovery. Historical data would extend the timeline and show long-term evolution. Perhaps the breakthrough will be collaborative. Teams combining expertise from radio astronomy, X-ray astrophysics, stellar evolution, and plasma physics might together assemble the complete picture. No single discipline holds all the answers. The solution might require integrating insights from multiple fields. Perhaps it will require patience. Some astrophysical mysteries take decades to resolve. Neutron stars were predicted in the 1930s, but not observed until the 60s. Black holes were theoretical curiosities until X-ray binaries revealed their presence. Long period. Transients might demand similar patience before yielding their secrets. The scientific process is not always linear. Progress happens through accumulation of observations, testing of hypotheses, and refinement of theories. Sometimes breakthroughs arrive suddenly. Sometimes understanding develops gradually over years. Either way, persistence pays off. The 44-minute source will not remain mysterious forever. Too many researchers are working on it. Too many telescopes are observing it. Too much data is accumulating. Eventually, someone will put the pieces together correctly. When that happens, textbooks will be updated. New questions will emerge. The discovery will open new research directions rather than closing the book. This is how science works. Answering one question reveals 10 more. Each solved mystery illuminates new mysteries beyond. For now, the source keeps pulsing. Every 44 minutes, 2 minutes on, 42 minutes off. Oblivious to human curiosity, indifferent to theoretical debates, it broadcasts into the void. We listen, we measure, we wonder, and somewhere in the data, in the observations yet to be made, or the insights yet to be realized, the answer waits. The 44-minute source will tell us its secrets. We just need to ask the right questions. The universe is patient. It does not hurry to reveal its workings, but it does not hide them either. Everything is there to be discovered if we look carefully enough and think deeply enough. This mysterious beacon, pulsing through the darkness across 16,000 light-years, is teaching us. We just need to learn its language. The next chapter in this story is being written now. In observatories around the world, telescopes point skyward, data flows, algorithms process, scientists analyze, theories develop, understanding grows, and one day soon, someone will finally say, "I know what it is." That day cannot come fast enough.